Arg, my calculator says overflow. I just need
3 to the 2002 modulo 7.
Breaking the firewall or failing math homework? Nice necklace, Tess. Actually, that necklace is exactly what Ata needs.
A necklace? I need a supercomputer, not jewelry.
Pierre de Fermat discovered a beautiful pattern in prime numbers. If A isn't a multiple of P, it looks like this. This is the key to your problem, Ata.
Okay, magical formulas, but why does it work? Is it just luck?
Imagine you have a bucket of beads with A colors. We want to make necklaces of size P. Step 1. Lay them in a line. We have A choices for each spot. So the total number of colorful strings is A times A, P times. Step 2. Remove the boring strings, the solid single color ones. We are left with the interesting strings, those with at least 2 colors. Step 3. Tie the knot. When a string becomes a circle, order matters less. If we rotate the beads, we get 5 different linear strings that make the same necklace. Crucial moment. Why does P have to be prime? Imagine P equals 4, not prime. Look at the pattern red, blue, red, blue. If I rotate it twice, I get the exact same string back. It repeats early. We can't divide 2 into a group of 4. There's a remainder. But since P is prime, you cannot break it into repeating chunks.
So for prime P, every interesting necklace comes from exactly P strings?
Step 4. The conclusion. We have A to the P power minus A interesting strings. Since P is prime, every necklace forms a group of exactly P distinct strings. This means the total number must be divisible by P. So A to the P minus A is a multiple of P, which gives us Fermat's little theorem. Let's verify with new numbers. P equals 5, prime, and A equals 3, colors, instead of 2. Can we divide 240 into groups of 5?
QED. Quite easily demonstrated.
Now, Atala, let's go back to your overflow problem.
So with 7 being prime, we know 3 to the 6th is 1 modulo 7.
Exactly. Now let's calculate 3 to the 202. Think about powers as cycles. Every 6 powers, we reset to 1. Round and round we go.
So I just need to see how many groups of 6 fit into 202.
Exactly. Reduce the exponent modulo p minus 1.
202 divided by 6.
Substitute that back into the power.
And 3 to the 6 is just 1, so the huge chunk disappears.
Now just calculate 3 to the 4. What is 81 modulo 7? Let's check.
That was fast. No overflow error.
So the answer to the code is 4.
1 lockdown. But here is the final challenge.
Final lock. It says, find x such that 3 times x is 1 modulo 7.
That's easy. X is 1/3. Done.
Not in modular arithmetic tests. We need an integer. We are looking for the modular multiplicative inverse of 3. Recall Fermat's little theorem again. We want 3 times something to be 1. Let's peel off 1 3 from 3 to the 6th. So 3 times 3 to the 5th is 1.
Oh, x must be 3 to the 5th.
Correct. Generally, the inverse of a is a to the p minus 2.
Let's calculate 3 to the 5th.
Wait, are you sure? Is 3 times 5 really 1?
It works perfectly. The inverse of 3 mod 7 is 5.
That's it. The safe works. We're in.
Well done on mastering Fermat's little theorem.